This chapter 2 introduces the Black-Scholes equation for pricing ordinary European options and examines some of the most important pricing characteristics of basic FX options. To begin with, we should specify that the formula we will be using for pricing a European FX option is actually called the Garman-Kohlhagen formula, named after the two individuals who derived it from the Black-Scholes formula for European equity options. The formulas are so similar, however, that people often simply refer to them both as the Black-Scholes formula. This worksheet GK requires you to input 6 items for an option to derive its price or premium. The 6 inputs are spot, the strike, the interest rate for the term currency, the interest rate for the base currency, the volatility of the currency, and the tenor of the option expressed in units of years. Spot and strike need no further explanation, nor should the two interest rates, except for one technical subtlety. The rate in each case should be quoted on a continuously compounded basis, a concept we explain in our modules on financial mathematics. If you have not completed those modules or do not remember what a continuously compounded interest rate means, it suffices to know that you can obtain it by simply taking the effective annualized interest rate and running it in Excel through the formula equals natural logarithm ln of 1 plus r, where r is the effective rate. To illustrate, suppose you know the annualized interest rate in US dollars, semi-annually compounded, is 5%. The effective equivalent of this rate as a first step is obtained in Excel simply via the operator equal effect open parenthesis 5% comma 2, where the 2 refers to the semi-annual compounding of the original interest rate, giving you an effective rate of 5.06%, and then applying the ln operator gives you 4.94%, which is the input you need in the Black-Scholes model. You need also to recall or to learn that the future value of $1 continuously compounded for t years at rate r is exp r times t, sometimes said orally as e to the power rt, and conversely, the present value of $1 discounted for t years at a continuously compounded rate r is exp minus r times t. Volatility, unfortunately, is a very complex concept for which we devote an entire, more advanced module. For one thing, it simply cannot be observed precisely, nor is it in reality constant over time. So what you input into the formula is some estimate of what volatility is expected to be over the life of the option, which may not equal what it has been in the past. Its strict mathematical definition is discussed in the dedicated module on volatility, but you can think of it as a reflection of how much the currency pair bounces up and down over time versus moving in a more predictable and smooth pattern. You can, however, generally assume that 1. Currency volatility is higher for free-floating currencies than for ones that are controlled to various degrees by their central banks. 2. All other things being equal, volatility is higher for emerging market currencies than for G7 currencies. And 3. It usually fluctuates between an annualized rate of 5% to 15%, for G7 currencies at least, and averages over the long term something close to 10%, a number we will use as our usual input in this module. Note carefully that you are asked to input in the model the annualized expected volatility of the currency, even if the tenor of the option is shorter or longer than 1 year. The rest of the model will take care of ensuring that the annualized volatility is adjusted for the actual term of the option. If you are given the volatility for a period T, which is not exactly 1 year, whether longer or shorter, you can convert that into an annualized volatility through the following simple formula. Annualized volatility equals volatility measured for period T multiplied by the square root of 1 over T, where T is expressed in units of years. To illustrate, if you are told that the monthly volatility of a currency is 4%, applying the formula above leads to an annualized volatility calculated as 4% times the square root of 1 over 1/12 of a year. Note carefully the double inversions, which of course is equal to 4% times the square root of 12, which is equal to 13.86%. It should not be surprising, obviously, that over 1 year a currency's volatility ought to be significantly greater than over 1 month. Note finally that we have also programmed into the model in cell D7 the outright forward rate for the currency pair. This is not an input, but is derived, as you can see, from the spot, the two interests, and the time to expiration, as you should be able to remember. While the forward does not play a direct role in the pricing of FX options, it is very useful to keep it in mind at all times as we review the properties of options that are in, at, or out of the money a little later in the module. The formula for forward in cell D7 is based on continuously compounded interest rates, as you should have noticed, to maintain consistency with the model. You would derive the exact same forward rate if you use discrete interest rates and the more familiar formula where forward is spot times 1 plus the term interest rate expressed as a discrete interest rate adjusted for the time divided by 1 plus the base interest rate adjusted for the time. You should finally note that the spreadsheet is written to provide the price in units of the term currency, i.e. US dollars, per 1 unit of the base currency, i.e. sterling. We begin by pricing sterling calls and puts under the following conditions: spot 1.5, strike 1.5, rate in sterling, the base currency, 5%, rate in dollars, the base currency, 5%, vol 10%, and tenor in euros, 0.5. The price for the call in cell G6 is the price per 1 pound sterling of notional expressed in US dollars. Thus, the right to buy in 6 months 1 pound sterling for a price of $1.50 is $0.0413, the premium paid up front, i.e. 4.13 cents per pound. For a 10 million sterling notional amount, we would simply use multiplication to derive a price in dollars of some $413,000. In fact, the exact number comes out to 412,609. Cell G7 gives the price for the put, which allows the holder to sell 1 pound sterling against $1.50. You may have noticed that since the two interest rates are equal, the forward is equal to the spot, and in this case equal to the strike as well. We describe a European option whose strike equals the forward to be an at-the-money option, whether we are talking about calls or puts. And more generally, we use the following terminology for the three possible alternatives. First, as we just mentioned, we call an option at the money, whether a call or put, if the forward is equal to the strike. We say that an option is in the money if, in the case of a call, the forward is greater than the strike, and in the case of a put, the forward is less than the strike. And finally, as you might expect, we say, in the case of a call, that it is out of the money if the forward is below the strike, and for a put, if the forward is above the strike. Note that we made no reference to the spot rate in any of these definitions. Many textbooks define the moneyness of an option by comparing the spot to the strike. But we think this is misleading and potentially confusing, particularly for European options that can only be exercised at expiration. Given this limitation on the right of exercise, what really matters is where the spot is likely to be at expiration, a level really best indicated by the forward rather than the spot. For American options, the alternative definition used in the textbooks is more defensible, since those types of options can be exercised at any time, and the gain upon such exercise would be strictly a function of the spot and the strike. Unfortunately, there is no consistency in how people define these terms, so the safe route is to always specify what you mean by saying in the money spot or in the money forward, or out of the money spot, out of the money forward, etc. In our modules, we always define a European option's moneyness by reference to the forward, unless otherwise specified. In most cases, particularly for short-dated options, the difference will be small, but it can become quite large for longer tenor options and in high interest rate scenarios. It is useful to introduce an approximation for the pricing of at-the-money European options, which allows you to estimate the price quickly, even in the absence of a pricing model. Here is the formula. Premium equals 0.4 times the spot times the vol times the square root of time, essentially discounted through division by 1 plus RT times T. T can be less than 1 year or more than 1 year, and you may need to make slight adjustments for compounding and so on. But this is intended as an approximation, especially for short-dated options. Applying this formula to our option, i.e. the one in the term sheet, would give us a premium per pound sterling of 0.0414, almost the exact answer we obtained earlier. But please remember that you can only use this formula for European options and only if they are at the money forward. Note also that this shortcut formula does not differentiate between calls and puts, which therefore must have the same price when they are both at the money. And this is confirmed in cells G6 and G7 of the worksheet if you wish to double check. This is an illustration of what is called the put-call parity principle, which says in its narrower version that a European put and call whose strikes are equal to the forward have the same premium. It should come as no surprise that increasing the spot, for example to 153, increases the value of the call and reduces the value of the put. The opposite happens when we reduce the spot. This property is intuitive and represents one of the principal uses of options by traders, namely to take directional views on the underlying while protecting their downside to a greater degree than they could if they simply bought or went short the underlying currency itself, since their maximum loss as owners of options is the premium. Returning now to the shortcut formula, it should be apparent that for an at-the-money option, the premium grows directly in proportion to volatility. So if I double the volatility, I should find the premium rising to double the original 413, i.e. to 8 cents, 0.26. In our worksheet GK, resetting the spot at 1.5 in order to have an at-the-money option, doubling the volatility gives us a price for the two options of 0.0825, which is very close indeed to the 0.0826 we had estimated with our shortcut formula. This is the other main reason for the use of options by traders: to take views on changing levels of expected volatility. If I expect vol to rise, I buy an option, while if I expect it to fall, I sell an option. Each of these positions, however, would include a directional view as well. So we would need to either incorporate this directional view into our trade if we are worried about a significant movement in the spot, or otherwise to neutralize it by means of various option combinations discussed in more advanced trading modules. The impact of an extension of the option's tenor, at least for an at-the-money option, is not quite as easy to visualize from this shortcut formula. We can see that the numerator grows by the square root of the tenor. So for example, it would grow by about 1.4 if we double the tenor. 1.4 being approximately the square root of 2. But we also see that the denominator will grow as well, giving rise to a lower present value for this numerator the longer the tenor of the option. For most options, the first effect dominates the second, which is why many people will say, although with some inaccuracy, that for an at-the-money option, the premium is proportional to the square root of the time to expiration. But you should now understand that this statement is, and always has been, an approximation and becomes significantly inaccurate for long-dated options. Indeed, we can see from our worksheet here that while an increase in the tenor of the options we are examining from 6 months to 1 year increases the values, and so on as we increase the tenor further, a maximum appears to be reached when the tenor approaches 10 years, after which any further increase in the tenor actually reduces the premium of the option. This is the point at which the impact of discounting the numerator for such a long tenor comes to dominate the increase in the value of the numerator as a result of the square root of t term. It may seem that these kinds of very long tenors are uncommon in practice, but we will see shortly that the declining premium phenomenon happens much earlier when dealing with currencies whose interest rates are far apart, and when we are no longer restricted to at-the-money options. We can summarize the properties of at-the-money European options that we have reviewed so far in this simple table. Thus, for calls, the premium goes up when spot rises and down when stop falls. For puts, it moves in the opposite direction as spot. With regard to vol, both calls and puts gain value when vol rises and lose value when vol drops. And with regard to tenor, both calls and puts generally gain value when we lengthen the tenor and lose value when we shorten it. But as we have seen, there will be exceptions to this last statement. We now turn to European options that are either in or out of the money. We can summarize their principal pricing characteristics via the following list. Unlike the case for at-the-money options, calls and puts that have the same strike do not have the same premium. If the call is in the money, the put, by definition, is out of the money, and vice versa. So the in the money option will always, or almost always, be more expensive than the other one, that is the out of the money option. Next point, just like at the money options, calls gain value and puts lose value when the spot rises, and vice versa when the spot falls. Just like at the money options, calls and puts gain value when volatility rises, and vice versa when vol falls. However, the relationship is no longer linear as it was for at-the-money options. And so a doubling of vol, for example, does not double the value of the option. In general, but as so often in the case of options, subject to some exceptions, out of the money options will gain value more than linearly when vol rises, while in the money options will gain value less than linearly. Next, just like at the money options, calls generally gain value and puts generally lose value when the tenor is extended, and vice versa when the tenor is reduced. But the almost correct rule that we mentioned previously, namely that the value increases by the square root of time, no longer holds at all and cannot be replaced by any elegant alternative. Regarding this last observation, you will recall that the at the money options we examined earlier did not begin declining in value until we had lengthened their tenors to some 11 years. With options that are in the money, this effect can be felt earlier and in some cases much earlier. Assume, for example, that we move the strike of our options to 125 and focus on the call. You will see that a 3-month call is worth 0.2469, while a 6-month call is worth 0.2440, which is slightly less. So the price has declined even though the original tenor was short and became only slightly longer. You may be able to intuit why this effect is happening so much sooner this time. You probably noticed that we made the call deep in the money to achieve the desired effect, so that it has become in essence, as of that point, a forward, given that it is virtually certain that it will be exercised at expiration. Therefore, its value is converging on the value of a forward contract to buy sterling on the same date as the expiration date as the option at 125, at a time when the current forward rate is actually 1.50, which would be equal to the PV of this $0.25 difference between the 125 level under the forward and the current forward level of 150. Please click on the pause button and confirm to your satisfaction that the PV of this 25-cent intrinsic value is 0.2438. Click play again when you are done. It follows from this observation that as we lengthen the tenor of the option, provided of course we leave all other variables the same, its value must decline since the intrinsic value stays the same but is discounted for a longer tenor, for a longer period. Remember, however, that in all of our examples involving a change in tenor, we keep assuming, unrealistically, that the applicable annualized interest rate remains the same. Things would be less straightforward if the interest rate for 3 months were different from that for 6 months, which of course is normally the case. We make one last but critical observation about the pricing of puts and calls that have identical strikes and other terms. If on this worksheet parity we set the spot, for example, at 155 and subtract the price of the put from the price of the call, we get 0.0488, which seems almost exactly equal to the 5-cent difference between the forward and the strike. In fact, if we discount these 5 cents to their present value, we get 0.0488. And you can see the formula here confirming that that's exactly what we've done. Taken the 5-cent difference between the forward and the strike and discounted using the continuous discounting operator by the 5% dollar interest rate, but adjusted for the tenor of half a year. So note the perfect equality between cell G8 and cell G9. This result can be written more generally as follows. The call minus the put equals the difference between the forward rate and the strike discounted. Each term is reasonably self-explanatory, but here they are. Call K means a call with a strike K. Put K, the same for a put. F is the current forward rate, K is the strike, R is the term currency interest rate, and T is the tenor of the option expressed in years. The reason for this relationship is quite simple, really. If you are long a call and short a put with identical terms, you will take delivery of the underlying at expiration under any possible outcome. If the spot lies above the strike, you will exercise the call, while if it lies below the strike, your counterparty will exercise her put. Thus your position is equivalent to a forward contract at this level K, since the outcome is absolutely certain. No more optionality. The value of a forward contract is simply the PV of F minus K, which is exactly the right-hand side of our equation above. This equation that we just wrote on this slide is the general form of the previously mentioned put-call parity principle. One of its implications is that the put price can always be derived from the call price, again assuming the same strike, and vice versa, simply by rewriting the above formula in the following two ways. Here's how you derive the value of a call if you already know the value of a put, and here's the derivation of the value of a put if you already know the value of a call. This concludes Chapter 2.